The one law older than physics itself is this: reality must make sense. Before Einstein, before quantum mechanics, before the discovery of atoms, humans believed that effects followed causes and time moved forward. But tachyons challenge that very foundation. These hypothetical particles, born from math, not observation, ignore our rules. They don't just move fast, they move backward through time. And here's the twist: if they exist, they may not just bend the laws of physics. They could point to an entire hidden layer of reality. Let's dive deeper. Einstein's special relativity hinges on one unbreakable limit: the speed of light. For any particle with mass, moving faster than light is impossible. That's because as you accelerate, your mass increases. To hit the speed of light, you'd need infinite energy. But tachyons aren't massive in the traditional sense. In fact, their mass is imaginary, a concept that comes directly from solutions to the equations of motion when speed exceeds light. Mathematically, this isn't nonsense. Imaginary numbers are used all the time in wave mechanics, electromagnetism, and quantum field theory. In those equations, a tachyon is a solution that appears when the energy of a system isn't minimized. A signal that something deeper is going on. Imagine the universe as a landscape, full of valleys and hills. A field that contains a tachyon sits atop a hill, an unstable point. It wants to roll down to a more stable state. In this way, tachyons don't just break physics. They reveal when it's incomplete. That's how physicists interpret them in modern theories. Tachyons aren't necessarily real particles. They're indicators, clues. They show up in unstable vacuums, or when a theory isn't in its lowest energy configuration. In string theory, tachyons indicate that the chosen vacuum, the background geometry of space-time, is unstable. Once the tachyon condenses, the vacuum evolves to a more stable form. So the presence of tachyons doesn't signal chaos. It signals transformation. This has led some to propose a wild idea: that the universe we experience today, with stable matter and consistent laws, is the result of tachyon condensation, a kind of cosmic phase shift. Think of it like this: just as water turns to ice at a certain temperature, perhaps the early universe froze into stability when the tachyon fields settled. But even more fascinating is what this implies for hidden dimensions. In theories like superstring theory or M-theory, there are more dimensions than we can see, sometimes 10 or 11. Tachyons may live in these dimensions, invisible to us, but still affecting the structure of space-time. Some physicists think tachyons may be connected to brane theory, the idea that our 3D universe is a membrane floating in a higher dimensional space. Tachyons could be vibrations in these extra dimensions, hinting at interactions we cannot yet observe. If true, this opens up the possibility of parallel universes connected by quantum fluctuations and tachyon interactions, a multiverse where causality is not fixed and time can flow in strange loops. But what if tachyons can be more than just messengers of instability? In some bold theories, physicists explore whether tachyons could be real particles, not just mathematical warnings. If they exist and can interact with normal matter, they might be detectable, perhaps in high-energy cosmic rays or in quantum field disturbances. But here's the problem: allowing tachyons in a theory usually breaks causality. That is, if you can send a tachyon message, you can send it backwards in time. Imagine receiving a message before it was sent. That leads to paradoxes, like telling your past self not to make the mistake that led to the message in the first place. Physicists solve this by restricting tachyons to be virtual. They can appear in calculations, but can't carry usable information. Still, some fringe physicists suggest that a hidden sector of the universe might allow tachyon communication, but only under special conditions, such as near black holes or in regions of extreme space-time curvature. Others wonder whether entanglement, one of the strangest features of quantum mechanics, might be tied to tachyon-like phenomena. In entanglement, two particles can be instantly correlated, no matter how far apart they are, a behavior Einstein called spooky action at a distance. Some interpretations hint that hidden, faster-than-light influences might be at play, and perhaps tachyons are the unseen hand guiding this connection. The idea is speculative, but in the search for a unified theory of everything, no possibility can be ignored. Whether they are real or not, tachyons push us to confront questions we often avoid. What is time, really? Is the future already written? Can the past be changed? Is causality a law, or just an illusion born from limited perspective? Tachyons may never be found in a detector, but their presence in the equations of physics and in the minds of those daring enough to question everything keeps the dream of deeper truths alive. Perhaps someday, with better instruments or new insights, we will catch a glimpse of that hidden layer and understand that reality is far stranger and more fluid than it seems.